Okay, carbon monoxide here. Let's draw the Lewis structure for acetic acid. Acetic acid also has this formula that you should get familiar with: CH3COOH. This is organic functional group that's discussed in chapter 3. What functional group is this? Carboxylic acid. So all carboxylic acids will have the carboxyl group with it. This is what we call the. This is not really the molecular formula. This gives a little bit of structural information. We have different types of formulas. Sometimes when you look at a formula like this, you don't get any structural information, and so they try to give you a hint of structure here. Is acetic acid what we call a monoprotic acid, or triprotic acid, or tetraprotic acid? Yeah, David's right. Monoprotic acid. Why isn't it a tetraprotic acid? It's got 4 hydrogens.
There's only one hydrogen. Is it because there's only one hydrogen that connects to oxygen?
Yeah, that's correct. Structurally, these hydrogens are different. And so this hydrogen we call an acidic hydrogen. These 3 hydrogens are non-acidic. And so if we were to write the correct, let's say, molecular formula, it looks like this, C2H4O2. Right? But here, you don't know. What is it? And we also have problems with isomers. You know what isomers are? What are isomers?
Same formula but different structure?
Yeah, same formula, different structure. And different structure means different properties. And so here we get a little bit of structural information, but here we get a lot of structural information. You can see these 3 hydrogens are clearly different than this hydrogen here. Well, anyway, let's take a look at the oxidation states. Now, somebody remind me the rules, because I was going through oxidation states yesterday with some people, and they weren't following the sequence. Now, why is it important when you're in chapter 3, going back to oxidation states? Why was it important to go through that sequence in order? And so I got this question yesterday afternoon about things. Like, for example, hydrogen peroxide. So if we're talking about oxidation states, what do you assign first? And so do you assign the hydrogen first or the oxygen first? Does it matter? The oxygen first? A lot of people will say the oxygen first, because then oxygen will give you -2, which makes hydrogen +2. But there's a big problem. +2 means it lost how many electrons? 2. But hydrogen can only lose 1 electron because it only has 1 electron, so it's impossible to lose 2. And so, if you wrote +2 for hydrogen's oxidation state, it's impossible. It can't work. So we assign hydrogen first, right? All right, then how about this one? Oh, hydrogen's got to be assigned first. It's +1. So hydrogen's +1. That means sodium is -1. And so do you see how the sequence is important in doing the oxidation states? Otherwise, you can get the wrong ones. And so taking priority over hydrogen are the group 1s. Group 1s get what charge? +1. And so in this case, hydrogen goes first, it's +1. In this case, sodium goes first, it's +1. And so as long as you have the rules memorized, it's pretty easy, the chapter 3 method of figuring out the oxidation states. For myself, I think it's much simpler doing it off Lewis structures, because oxidation states, you only have one rule, and what rule is that? The one rule is winner takes all. That's it. And then you don't have to worry about memorizing. What was that sequence again? Yeah, actually the sequence is easy to memorize once you do a bunch of them. you know, but in chapter 3. But, you know, all that work, memorizing that sequence, and still, it's not great. Still, it's not great because, let's take a look at acetic acid. Actually, let's finish hydrogen peroxide. What's oxidation state?
-1.
-1. I know people, yeah, I think I got to write bigger because, +1 and -1. What do I got here? Why isn't it -2? I have 2 oxygens. You know, one of the most common errors that I see, people will say it's -2 because I have 2 of them at -1, and that gives me -2. Well, -2 is not right. What is -2 called? The net negative charge. You know, the total negative charge. I don't want the total negative charge. I want... Yeah, and what is the definition of oxidation state? If somebody asks you, what is an oxidation state, what would you tell them? Give them a simple answer.
The charge of a single.
Yeah, the charge on an atom. It's the charge on the atom when we make the assumption. What was the assumption? It's the charge on the atom when you assume. Now, Priscilla?
100% ionic.
Yeah, 100% ionic. What is formal charge? It's the charge on an atom when you assume 100%. What is the real charge on an atom? Because, you know, sometimes formal charge gives you a conflict. Because formal charge here is 0. Formal charge here is 0. I don't want to draw out the Lewis structure for this, but there's a conflict here. Well, obviously, there's going to be a conflict because one assumes one extreme, the other assumes the opposite extreme, right? And so what we're doing is we're bordering the range. The charge is never going to go higher than +1, and the charge is never going to go lower than 0. It's the actual charge depends on what the percent ionic character is in a bond. Do you remember the chart where they showed percent ionic character versus delta En in chapter 10? Do you remember that chart? It looked like this. Percent ionic character versus delta En. And they plotted out, you know, the percent ionic character is determined by different things. Is this, if you look at the data, would you say it's well correlated, the percent ionic character? No. We have a value that we can measure. If delta En is 0, then what is the percent ionic character? Give me a molecule where delta En is 0. Get them mixed up again. O2. Yeah, what do you expect in an oxygen molecule? Do you expect any ionic character? You know, who's the winner? The left oxygen or the right oxygen? Neither. It's got to be a tie. I mean, it's impossible that winner takes all in this case. Does that make sense? And so what is the percent ionic character? It's 0. And so, okay, we got some zeros there. But the rest of this is, there's a rough correlation here. You know? The rough correlation looks something like this. And sometimes with rough correlations like that, we measure there's a correlation. Have you ever heard of the R² value? R²? Somebody remind me what R² is. Or the range of values of R². What's the best R² value you can have? The best R² value would be 1, you're right. R² value of 1 means what? Paul? All the dots are right on the line. Do you see all the dots right on the line? No, guesstimate the R² value for me. Give me your best guess for an R squared value. 0.7? Yeah, I'd say, you know, maybe 0.7, 0.8 maybe. Yeah. A 0.7 or 0.8 R squared value, is that good in science or not so great? It's not so great. In the social sciences, I was reading some papers where they're talking about R squared value of 0.6, and you look at the data, it's scattered all over the place because human behavior is hard to map out. But, you know, that's good maybe for talking about human behavior, but for talking about science, and, we want R squared value. What kind of R squared values do we want? This is, you know, you got to know the numbers. If somebody said, I got an R squared value of 0.5, what would you think? You think garbage. And usually when I see a 0.6 R squared, I think garbage. There's no correlation there. You know, 0.7, maybe this is a little higher because it was a decent, semi-decent. But what this says is that the percent ionic character is roughly correlated to delta En. The bigger the difference in electron negativities, the more polar it's going to be. And the more polar it is, the more percent ionic character it has in that bond. And it's a decent correlation, but it's not perfect. So what does that tell you? It tells you that delta En isn't the whole story. If delta En was the whole story, you'd get an R squared value of 1. It'd just nail it. Right? And so we got to think, you know, well, there's more to bonding than just delta En. And so when you think about the details of bonding, you know, then if you want to know bonding, what do you have to know well? The theory of bonding. And if you want to know the theory, because theory is ultimately what we're after, because what is the theory? Theory would be the fundamental picture of bonding, right? The fundamental description of bonding. What is a bond? And what are the mechanics of bond formation? All that. That's the theory. Now, what is the theory of bonding? You know, this is all stuff from Chem 1A. These are the important things that you should know from Chem 1A to carry on to higher level classes. One of the most important things is bonding. This is why I spent so much time in Chem 1A talking about bonding, valence bond theory, MO theory. Because why? Because molecules are so important. Not only molecules, but ionic lattices, metallics, solids, etc. All those deal with bonds, and I think you all know the bond, but you know, we just want to make sure we got the jargon correctly, because people know MO theory, they know valence bond, but sometimes you ask them, what is the difference? I've asked lots of students, what's the difference between valence bond theory and MO theory? And they draw blanks. And so I thought, okay, if they're drawing blanks, then how can I reinforce this point that they got to know the difference? I mean, how can you get through without knowing the difference between valence bond and MO? Right? What exactly is the difference between it? Because it's okay to use it, you know, if you're just being paid to mechanically punch buttons or mechanically do this, and you don't have to think about it. But if you have to think about it, then if you're going to use it, you better know what it means. If you're going to use the ideal gas law, then you better know what an ideal gas is. Otherwise, that's trouble, because you do a calculation using ideal gas law and your data comes out different. Why? You know, why are my numbers different than what I just calculated in ideal gas law? And so this is just repetition. So I know it's still because I've taught 1B so many times, it still draws blanks. Even though I talk about it so many times in 1A for my former students, it still it doesn't quite click. So we'll just keep hammering. And so what is the theory of the bond, the chemical bond? Well, really what the theory is quantum mechanics, right? Quantum mechanics. But quantum mechanics applied to bonds, is either called valence bond theory or MO theory. Now, what's the difference between valence bond and MO? Give me a brief, just crude. Yeah, David?
The lowest molecular orbital theory is the LCAO.
Yeah. Okay. Okay, that's good. A bond is, how does MO theory describe a bond? Remind me how MO theory describes a bond. What is a bond in MO theory? If I have atom A and atom B here, how does MO theory describe a bond? How does MO theory describe a bond? And so this is, you should be able to answer that, right? Stephanie?
As stretched across the entire molecule, belonging to the molecule itself instead of to the individual atoms that make it up.
Yeah, that's a key part of MO theory. But, stretching across the molecule doesn't quite give me a visual picture. A theory should give you a visual picture of what's happening, why a bond is a bond. A theory is supposed to be a description, a fundamental description of a bond. So a fundamental description is what's holding the carbon and the oxygen atoms together. This is a triple bond. It's hard to break. But what's holding them together? That's what I want out of a theory. I want to see this visual picture, and this is why I drew so many. And I know I got the pictures sometimes got messy, right? But it was just to show you, because this is theory. Theory is supposed to give you this kind of visual picture of what's happening. And so what's happening? Why did I draw? I'm just asking former students, why did I draw that? Just to see where I need to go. Next time I do one. In other words, you go, okay, that's a messy drawing on the board. But what was the point of that messy drawing? What was, the key take-home point? This is what I mean by, when I was a student, I did a lot more than just review my notes. Every day after class, right after class, because the classes I had pretty long breaks. Every day after class, this was at UCLA, this was my routine. Every day after class, I'd immediately go to, there's a coffee shop, the Kirchhoff coffee shop. Sit down at a table, grab a cup of coffee, and then go back through my notes. And there were lots of blanks because they talk so, a lot of the professors, they talk so fast and they don't write anything on the board. And so for my memory, I try to fill in as many blanks as possible in my notes because I had lots of blank spots, where I couldn't, I'm not a fast writer. They say if you want to get an A then learn shorthand. If you want to get an A, if you can learn shorthand, then you pick up a lot more information out of lectures. And so I never learned shorthand. But at least the short-term memories was okay for a certain point. And so this is why I did it immediately after, because my short-term memory would fade. And they've done, studies. They've done studies where after like 2 hours, how much of your short-term memory you've just lost?
50%.
It's a big number. So this is why it was critical for me to do this right after class, because it just fades so quickly. And so right after class, I'd start writing all the stuff that I remember, but I couldn't write down at the time because it just kept going. And then I'd have the book. I'd have the book there, and I never read the book before class. I always read the book after class. In fact, that's when I started reading the book. And I would only focus on the sections that gave me trouble. And the sections that gave me trouble, I read very carefully. The sections that I found easy, in lecture, I'd just skim through those. And then I'd fill in the notes, and then I'd annotate it. What was the take-home point here? Was there a take-home message? Because sometimes the take-home message wasn't given. You can't always say. And so then I'd write down the take-home message, because writing down the take-home message for me made me remember it a lot easier, than just memorizing somebody's take-home message. If somebody said, okay, this is the take-home message, then typically it's not as ingrained into your memory as saying, okay, this is my take-home message in my own words. And so I say winner take all, but how many people remember that? Winner take all. And so what you got to do is you got to come up with your own visual picture of what's happening. Whether you want to say, okay, you come up with some other method if you don't like that. And so this is what I do. I come up with another method because let's say I didn't like that catchphrase that the professor used. I come up with my own. And then I remember it. And so if I come up with a big messy drawing up here, then, okay, you get caught up. That's a messy drawing. There's no way I'm going to copy that. It's just, and then forget it. But no, you shouldn't forget it. You should come up with your own take-home message. What was the take-home message of that? And so after that messy drawing, I said, okay, this is how MO theory describes a bond. How does MO theory describe a bond? And MOs. Stephanie has it right. The MOs are big. They span the whole molecule. But just because we have MOs doesn't tell us we have a bond.
For the exact number of atomic orbitals that were combined, you have the same number of molecular orbitals combined, one bonding, one anti-bonding?
That's correct.
Okay.
That's part of MO theory. But, just because we have a bonding and an anti-bonding MO doesn't mean we have a bond. What creates the bond? We have lots of empty MOs. The great thing, I'll tell you about MO theory. One of the things about MO and valence bond, do you know the limitations of valence bond? Somebody tell me the limitations of valence bond. For sure, it didn't work for oxygen. Okay, valence bond, yeah, but that's not really a limitation. That's actually a tool that we can use, so it's a helpful tool. It only reaches an octet, and we could expand the octets if we, do some extra stuff. But that's good to think about that in that way.
In valence bond, the orbitals are still separated versus molecular orbitals. Kind of look at it as a whole.
Yeah, that's true too. That's true. But those aren't really, what's the limitation? What's the limitation? Okay, in valence bond, actually, we aren't limited to an octet. In valence bond, we could take advantage of what were those? Empty d orbitals, and then throw some extra electrons. Remember that? The hybridization. If you did expanded octets, you might have done something like sp3d or sp3d2 hybridization. Did you guys do that?
Yeah.
Starting last semester and over the summer, I decided to decrease the amount of that. I do, but we can expand octets and still get it. Except, Petrucci, that's one of the other limitations of valence bond theory. Valence bond theory, let me tell you that valence bond theory uses those Ds. And so we get sp3d, sp3d2 hybridization. But the data that is the full molecular orbital theory shows that the hybridization of the Ds is very limited. And so at the end of chapter 10, they talked about, do you remember at the end of the chapter 10, there's one section, or chapter 11, there is one section that talked about the limitations of valence bond theory. And one of the limitations is this. When we have something like this with an expanded, let's go to PCl6. Or let's do SF. Let's do SF6. I think that was the example they used in that chapter, SF6. Do I want to do this? I'm spending way too much time on Chem 1A stuff. Unless you want to. Do you want to hear this? Or
Yes.
maybe we'll skip it. But do you remember SF6 as this? How many valence electrons? What is this? Is this an octet? In the valence shell of sulfur, how many electrons do we got?
12.
12. How can we fit 12 electrons in there? In the valence shell of sulfur. We take advantage of the d orbitals, right? And when we say that sulfur is sp3, what's the hybridization of sulfur here? D2. And so we have these sp3 D2 orbitals, And in valence bond theory, we got an sp3d2 orbital here on sulfur overlapping with what orbital on fluorine? sp3. And so we describe this bond as an sp3d2 sigma bond. And so let me tell you the way valence bond theory explains what a bond is. Valence bond theory says this: when you have overlapping orbitals like this, you're going to have concentrated electron density here. If we have concentrated electron density here, then the nuclei in fluorine and the nuclei in sulfur are going to be drawn to this negative charge density here. If they're drawn to the negative charge density, it's going to hold the two nuclei together. And so this is the way valence bond theory describes a bond as overlapping atomic orbitals, concentrating electron density, which causes the nuclei to be held together, that negative charge density. Well, that last section of that chapter started to talk about in the full quantum mechanical bonding theory. The full quantum mechanical bonding theory is MO theory. Valence bond theory I called quantum mechanics, or what did I call it? Quantum mechanics light. It's light because you make some assumptions to simplify things. And sometimes those assumptions aren't 100% accurate. And so sometimes you don't want the full version. You don't want all that confusing, difficult calculations. But there are some things you got to sacrifice to use the light version. One of the things you sacrifice is you cannot calculate the, what do we call when light interacts with matter? The study of light interacting with matter and then drawing a little graph showing how light of different wavelengths interact with matter. Yeah, spectroscopy. And so one of the things we like to do is we'd like to predict the spectrum of molecules, not just atoms. We did atomic spectra. Do you remember that? The hydrogen atom, etc., helium. We did molecular spectra too. Do you remember what molecule in 1A? I think everybody does this. So think back. What molecule did we generate a spectrum for using the UV Vis Spec 20 spectrometer, spectrophotometer? What molecule is that? Starts with we could use just the generic name. Starts with an R. Yeah. Marlon. What was it again? Red food color. Erythrocene B. Remember that molecule? And they gave a peak in the... Well, what was that peak caused by? That peak was caused by light shining on the molecule of erythrocene B. And what does light do? Visible light do? Excites electrons. And so when we're using valence bond theory, we shine light on this. Where do the electrons get excited to? Which orbital does it go to? It's got to go to an empty orbital somewhere higher. Yeah, maybe it goes into the 5s, 5p. Maybe it goes. Is there such thing as a 99d orbital? Does a 99d orbital exist? If somebody asks you, hey, does a 1 million p orbital exist? How about a 3 trillion d orbital? Does a 3 trillion d orbital exist? Paul, you're saying yes?
Yep.
Yeah? How about a 1 trillion I orbital? Does a 1 trillion I orbital exist? There's an I orbital? Is there an I orbital? Or am I just making this up? J orbital. How about the J orbital? How many orbitals are there in an atom? You're saying infinite, Stephanie? Somebody else tell me. How many orbitals are there in an atom? Well, Stephanie's right. There's an infinite number of orbitals. If there's an infinite number of orbitals, you better start naming them. I mean, if we start at S, P, D, F, you know, where do we go after F? We got to go to G. Where do we go after G? H, I. So does an I orbital exist? Yeah, sure it does. You know, after we run out of all the alphabets, then we got to go double A or something. We got to make up some other system, because how are we going to number all infinite orbitals, right? Oh, what was I talking about? I forgot.
Charge density.
I was talking about promoting. So, oh yeah, where do I promote the electrons here? Well, maybe it goes to a 1 trillion I orbital, but that's an atomic orbital, right? And it turns out that, you know what, valence bond theory cannot predict the spectrum of this. It can't look at how many transitions we expect. MO theory does predict it, because, you know, if we have an electron here, we just promote it up to here in one of these empty ones here. And there are a whole bunch of rules that govern that, because you can only transition from certain types of orbitals to other types of orbitals. In the full MO theory, you only got a peek at MO theory. In the full MO theory, they start to subdivide the MOs. They subdivide it depending on the spin. You know, it was a spin like this, a spin like that, you know, and they subdivide it based on symmetry and other things. So they get a whole bunch more lines. But anyway, so that's one of the many limitations of valence bond, but there's a huge advantage to valence bond. And I was asking this question earlier, why wasn't valence bond theory abandoned? So do you guys have the answer? Because somebody mentioned what the answer was, right? What is the answer? Yeah, it's easier. It's easier, even with all the limitations. Why don't we use the van der Waals? Remember the van der Waals equation for calculating gas pressures, volumes, etc.? Remember that? The van der Waals equation for real gas? Why don't we use the van der Waals equation for real gas for every single gas? Because that would give us a more accurate answer. And so what we should do is we should abandon the ideal gas law, because the ideal gas law is for an ideal gas, and an ideal gas, is it fiction or real? It's fiction, right? There's no such thing as an ideal gas. And so why do we even bother using the ideal gas law? We should just dump that, like Bohr theory, into the garbage can of scientific waste. No, Bohr theory is actually, I shouldn't be so harsh on that, because Bohr theory conceptually is easy to see and visualize, so I understand why they continue to teach it. But why do we still use the ideal gas law when we have so much better equation? The van der Waals equation, which is so much better, so much more accurate. Did any of you do volume calculations using van der Waals equation? I know my students did, because I wanted them to see that the van der Waals equation is not so easy. In fact, it's kind of hard to solve, right? Because you have to use the method of. Are you guys familiar with the method of successive approximation? If you're not, you're going to be, because in science we have to start approximating a lot of things, because the calculations get very hard. And even in quantum mechanics, these calculations for MOs, accurate calculations, is so hard that, you know, the errors, you know what the errors associated with these are? If you were to do like the error bars, you'd see the error bars are, because these energies are quite small, and the errors are kind of large, so, you know, there's big errors associated with this. You know, this energy can be here, because you make so many approximations in solving this. You know, quantum mechanics can only be solved exactly for what atom? For the hydrogen atom. Everything else has to be solved by using techniques like successive approximation or simplifying assumptions. Have you ever heard of simplifying assumptions? Well, we've used them. You know, we simplify gas into an ideal gas. That's a simplifying assumption. We're gonna say oxygen is going to behave ideally. That's a simplifying assumption. So we use simplifying assumptions a lot to help us with our calculations. And so once you've done the van der Waals and you tried to solve it for volume, then you know why you want the ideal gas law. You know, because it's a heck of a lot easier. Actually, you know what, though? Was that all that hard, that simplifying assumption? No, it was easy. It was just time-consuming. And so I shouldn't say hard, because I don't want to give you the wrong impression. It's just time-consuming, that's all. So, I mean, like Michael was saying, you know, this is the easiest class, but it's hard. It's easy if you study a lot. Yeah, that makes it a lot easier. But studying a lot means it's hard because you got to work hard to get it. All right, so how would you describe MO theory? Let's look at carbon monoxide. That's a good one. How would you describe MO theory? With valence bond, this is easy. Valence bond, you know what a triple bond is. What's the hybridization here? SP, this is? SP. And so a triple bond is an SP-SP sigma overlap. SP-SP sigma P pi and a second PP pi. So we got two PP pi bonds and one sigma bond. That's a triple bond. And we can kind of map out the density. And so, you know, the sigma bond is going to be in here. You know, we got the SP sigma bond. We got electron density here. And then the PP pi bond is going to look like this. We got a p orbital here, let's say in the plane. And we got electron density here, electron density here. And so what's going to happen is the nucleus is going to be drawn to this electron density here. The nucleus is going to be drawn up to this electron density here and down to this electron density here. And net, the nuclei are going to be pulled together. Where's the second PP pi bond? I just drew one PP pi bond there. Where's the next PP pi bond?
Yeah.
Coming out of the board. And so coming out of the board, that's tricky to draw. And so I'm going to use the Petrucci perspective. I do it differently because but we'll try to draw the Petrucci perspective like this, coming out. I shouldn't have done blue, but I'll color the electrons differently. And so one of these p lobes sticks out like this. The other p lobe sticks in, so I'll dot it. And then we got electron density here and here. And so that electron density, well, it's going to pull it up like this and pull it up like this and then pull it in, pull it in. And pretty soon the drawing looks pretty messy. Right? But what's the point? The point is we got a lot of electron density. We got electron density in the internuclear axis, which we call sigma electron density. And we got electron density outside the internuclear axis, which we call pi electron density. And that electron density is what holds the two nuclei together. Well, that's a valence bond. How about MO? In MO theory, you know, here's, let's say carbon's over here, oxygen's over here. We got these new orbitals, right? And one of the new orbitals we have is the sigma 2s orbital. And we got two electrons in that, and so we got electron density here. This is a good orbital because electron density is going to hold the nuclei together or not. It's going to hold the nuclei together. Right? What comes after the sigma 2s? Sigma 2s star. So how many electrons do we have in the sigma 2s star? 2 electrons. In the sigma 2s star, is that good for bonding or bad for bonding? This is obviously bad for bonding. You know, there's nothing holding it. In fact, the sigma 2s star is exposing the nuclei, and so it's not helping. And then what comes after the sigma 2s star? Now, the carbon monoxide is kind of funky. Do we use the high Z MO or do we use the low Z MO? See, that kind of memorization you wouldn't necessarily have to do. Usually, for I don't even know if I want to talk about it. Does somebody remember? What would your guess be? You know, did I tell you that some books don't even have a high Z and a low Z? They make a simplifying assumption. The simplifying assumption is, why bother memorizing a high Z or low Z because you're going to get approximately the same answer. And so that simplifying assumption is kind of like the valence bond. Why do all the complication of MO when you're going to get approximately the same visual picture of what's happening with electron density? And so the way, the way I learned MO theory, the way I learned MO theory was the more electronegative species will dominate the MO. And so the more electro would be oxygen, so we'd use the MO diagram for oxygen. The MO diagram for carbon is different, right? And so what was the MO diagram for I don't really want to do this. Maybe I'll just do this real quick. But remember the two MO diagrams, sigma 2s, sigma star 2s, and then we had the sigma 2p. This is the expected. This looks very logical. Pi star 2p, sigma star 2p. But something funky happens with some atoms. The funky thing that happens is that the sigma 2p gets bumped. Where did the sigma 2p go? Between the pi 2p, so we got the sigma 2p here. I want to ask this question. Why the difference?
Sigma 2p is more penetrating.
Okay. Well, penetration has a lot to do with it, but you can't just leave it at that because, okay, so what? Why does it make him higher in energy? It's because why? Actually, this is a question I just asked. What was it? 2 weeks ago? Was it, David? Three? Has it been 3 weeks already? This is a question I asked in summer. This was a quiz question. Why the difference? Or was it the final exam? So it was on the final exam.
Yeah, it was on the test right before.
And it was on the test right before. So, yeah, this is the final exam question. Why are these different? And, yeah, penetration has a lot to do with it. And so this we call the high Z or the low Z? This is the high Z. Is this the low Z or the high Z? This is the low Z. If that's the high Z, this has got to be the low Z. And so you can't just say sigma 2p is more penetrating. If it's more penetrating, it should become more stable. This is why the 4s, remember yesterday I asked you, why is the 4s lower in energy than 3d when it's farther from the nucleus? When something's farther from the nucleus, it should be higher in energy, not lower in energy. And so if the 4s electron, the most probable distance for a 4s electron, let's say, is 16 times. R0. And for 3, it's 9 times, right? Yeah, 9 times, R0. Do you guys know where I'm getting those numbers? where I'm getting those numbers is one thing that came from Bohr that is still applicable in quantum mechanics is this, for the hydrogen atom, I'm saying. For the hydrogen atom, we apply it to everything else, so I'm just saying these are approximate. But the Bohr orbit, the radius of the Bohr orbit is equal to A naught times n squared. And so do you remember the Bohr orbits? The first Bohr orbit is going to be at 53 picometers, or 53 or 54 picometers? Where's the second Bohr orbit going to radius? Yeah. The second Bohr orbit would be 2 squared, 4 times A naught, or R0, or R1, I should say, R1. And this one, it turns out that the electrons don't orbit there, but that turns out to be the most probable distance of finding the electron from the radial probability function or the radial distribution function that we talked about the other day. Well, anyway, I was taught, when I was taking MO theory, I was taught that oxygen would be dominant because that would be lower, and I thought the calculations verified that. But looking at the MO diagram in Petrucci, you know which one he used? He used the low Z for this. And so the next orbital after sigma star 2s would be not the sigma 2p's that you'd expect, it would be the pi 2p's. And you know what? I'm not going to talk. If you care about why this popped up, you can look it up. But that's Chem 1A material. It's not going to be so critical for us for 1P, but it's important. You should know that. Why you should know that? Because we care about the energies of orbitals, and what impacts the energies of orbitals is we care about electron density. And we want to map out electron density in molecules as accurately as possible. That's why you should care about it. And so you got to go back. It has to do with shielding and penetration. You're right. Sigma 2p is much more penetrating, and so sigma 2p being more penetrating can get away from the sigma 2s's. Actually, no, that's wrong. It's the sigma 2s is more penetrating. And since the sigma 2, well, just to follow up, 1 minute explanation. A sigma 2s is more penetrating, and so it gets pulled towards the nuclei and shrinks. A sigma 2p is less penetrating, and so it doesn't get pulled as tightly. And so the sigma 2s shrinks down like this, the sigma 2p is like this for high Z. For low Z, penetration isn't as significant. And for low Z, the sigma 2s doesn't get really pulled in tight because the nuclear charge is lower. And so the sigma 2s is like this, and the sigma 2p doesn't get pulled in tight because Z is kind of low. And so the sigma 2s and the sigma 2p occupy the same volume of space around the nuclei. If they occupy the same volume of space around the nuclei, what's going to happen? Repulsions. And so they get bumped up. These sigma 2p's get bumped up because of the repulsions with the 2s. Yeah, I just remember talking about that 3 weeks ago. Anyway, so what comes next? Well, Petrucci, in that chapter, he shows, for carbon monoxide, he shows the low Z. And so what orbital comes next? Pi 2p's. We got 2 of them. What do they look like? Well, one of them is like this. And so we got electron density here and here. Actually, let's fill this. How many electrons does carbon monoxide have? Carbon is 4, right? Oxygen is 6. So 10 electrons is correct. Good. 1, 2, 3, 4. And then how do I fill the pies?
One each.
1 each, undrill. And then pair. 2, 4, 6, 8, 10. And we're done. And so we got two electrons in this. Where's the other pi 2p? I drew this picture, very similar picture to this. Look back in your notes for oxygen, O2. For O2, though, we use the high Z. Okay, what comes next? The other pi 2p. Where's the other pi 2p?
Coming out.
Coming out. And so let's try to draw it in perspective. So I'm going to shade it. One lobe coming out. And then the other lobe sticks behind the plane of the board, like this. And then we have 2 electrons worth of density there. Now, the pi 2p's, is that going to help or hurt bonding? It helps, right? Because the pi 2p's, the nucleus is going to be drawn to this green cloud here, this green cloud here, and down to this green cloud, and down to this green cloud. And it's going to effectively pull in. Is the pi going to be better at drawing in the nucleus or worse than drawing in the nuclei than a sigma? It's going to be worse, right? We expect sigmas to be better than pi's. And that's the case. It's easier to break a pi bond than it is to break a sigma bond. All right, after that then comes what? After the pi's, we fill the pi's, then what do we fill?
Sigma.
The sigma 2p. Now the sigma 2p is going to look, let's pick a different color. Okay, now this is low z, so the sigma 2p and the sigma 2s occupy kind of the same volume of space. This. This is not the greatest drawing, but a little bit better. It's because, you know, even though the sigma 2p is less penetrating and the sigma 2s is more penetrating, they kind of occupy the same because the z is kind of low. And since we have a low z, it doesn't really pull in the orbitals. With a high z, do you know what's going to happen? The sigma 2s, which I drew in black here, oh no, not black, what did I draw it in? Blue here. The sigma 2s is in blue. There. With a high z, well, the sigma 2s is more penetrating, so with a high z, what's going to happen to the sigma 2s? High z. It shrinks down. If it shrinks down, then it gives the sigma 2p's more breathing room. Because the sigma 2s's are confined to a smaller volume. Here, there's not much breathing room. You know, the sigma 2s electrons and the sigma 2p electrons are trying to occupy the same volume of space. And there isn't enough space. Well, anyway, we got 2 electrons in the sigma 2p. Oh, this is purple. Are those going to help? Oh yeah, they're going to help. And so what describes a bond in MO theory? Tell me what a bond is in MO theory.
Numbers of bonding orbitals versus the same.
Right. In other words, you know, in MO theory you have a simple calculation. And so this is the difference between a person who punches a calculator. A person who punches a calculator does this. They count the number of bonding electrons. 2, 4, 6, 8. Minus the number of antibonding electrons. 2. So 8 minus 2 gives me 6. Divide by 2, they get a bond order of 3. Anybody could do that. Anybody could be trained to do that, right? And so that's nothing special. You know, and I'll tell you, you know, I hate to you know, science is great just to learn, but a lot of you obviously want to get some kind of job with this. And, you know, with global competition, everything's getting more and more competitive. And so do you really stand out as a scientist? Because nowadays you gotta be able to stand out in order to be noticed. Because if all you can do is just punch, I calculated my bond order, it's 3. That's not enough nowadays. I've heard about my friends interviewing, and it's much more. They want much more, And how do you get much more? Well, if you have 30 years experience, or you got certain experience. But you got to think about this, and so this is why there's always that big push for critical thinking. That critical thinking component, because that's one of the things that they test on. Are you a button pusher, or do you think about it? So your button pusher, the bond order, that's such a simple calculation. Bond order, 3, magnetic properties, diamagnetic, I'm done. Done with that. And so, based on friends' experience, it's tough to get a job. It's demanding because you get a lot of competition. Hopefully, the economy turns around and things pick up, and then it's easy to get a job. It fluctuates. And so by the time you're finished with your science, you can pursue whatever, grad school, medical. Even in my friends who went to medical school tell me about their oral exams. Like, this is some bizarre questions. Like, if you had a boat and there were 7 people, one of them was non-ambulatory, couldn't walk or whatever, and you had to get them all across the river. How would you do it? Something like that, and the minimum amount of, it was just going, what? And there's some other trick where, you couldn't get everybody across the river. And so who was left behind? Something like that. It's a weird question. But anyway, that... So here, you got to think, okay, what is a bond? If you want to, in theory is what we're all after. Theory should give us a visual, a description, mathematical, visual, whatever description of what a bond is, as fundamental as possible. And so tell me what a bond is as fundamental as possible. Yeah, more bonding electrons versus anti-bonding, right? But how does that help hold the nuclei together? And so how does it help hold the nuclei together?
Concentrates the charge density between the nuclei.
Yeah, that's the kind of answer I like. Yeah, we got more dots here between the nuclei than outside. The antibonding curve, and so we got more electron density in the internuclear region here than outside in the antibonding. Then we got a bond. And we can figure out the strength of the bond depending on how much electron density. So we have how much electron density? 2, 4, 6, 8. We got 8 electrons worth of density here. So shouldn't that be a quadruple bond? You would think so, but these 2 electrons anti-bonding cancel out one of the bonding pairs, and so we only end up with 6. Well, 6 electrons is a triple bond. And so that's that kind of thing. We want to start thinking, and we want to analyze things in that way. So I'm going to stop here. We'll take a break. Or actually, no. Let me, since we're already. Let me just talk about. Unless, can you wait another 10 minutes? Or actually, another 5 minutes. Oh, let's wait another 5 minutes, and then what I was thinking, we'll just take a longer break, 15-minute break. Rather than, all right. I understand though that it's hard to get everything the first time, and that's the nice thing about science is it's kind of repetition. I mean, you lay the groundwork and you just keep repeating it. Because do you think the theory, if this is the theory of matter, do you think it's going to change? No. And so we just learn new applications for it and keep building up from there. All right, now, are we going to analyze every molecule like this? No, that's a pain. And so what we need some rapid ways of figuring out how the electrons are distributed in molecules. Do you know the rapid way of figuring this out? This is a pain in the butt. Right? And not only that, we need to do calculations. You know, what is the positive charge density on carbon? Actually, is the carbon positively charged or negatively charged? You know, what about the oxygen? So negative, positive charge density on that? We'd have to do calculations. And quantum mechanical calculations, you need a computer to do that, except for hydrogen. Hydrogen you can do by hand. It's not that hard. If you've had calculus, differential equations. And so we don't have a computer. We have to do things on pencil and paper. And if we do things on pencil and paper, then what are the tools we have to get some kind of idea of how the electrons are distributed in atoms and molecules? What are the tools that we can use to get some kind of idea about how the electrons are distributed? The valence bond theory, but you know what? Valence bond is too much. I want something more rapid. You know, I want to simplify my life like the ideal gas law. I want something easy. What's easy to do, very easy to do, and gives you some kind of rough picture of how the electrons are distributed in that. Lewis structures and Lewis structures are kind of based on valence bond theory in a way. You know, the Lewis structures are based on valence bond theory. Valence bond theory doesn't handle like resonance and hybrid structures, so we have to add that later. Right. I mean, Lewis structures, you end up with, let's say, a double and two singles. In MO, you'd never end up with a double and two singles. What you'd end up with is 1 1/3 bond order on each of those. And so for valence bond theory, we have to add an extra step to get that, the hybrid, right? But you know what? I don't want to even think valence bond. I want something even easier. So what's even easier? Why do I care about electron density? I care about electron density because that's going to tell me how things behave. You know, I want to know the structure so I can make predictions about it. But I don't want to do the full quantum mechanics because I don't want to have to punch every single thing I need into the computer and have the computer spit out an answer for me. I want to be able to think myself, so I got to simplify things. How can I simplify things to make my life easier to understand electron density in atoms and molecules? Ions. Huh?
You can draw that.
Yeah, I'll draw them out. Done. So it looks like this carbon has some electrons around it, an octet. This oxygen has an octet. And an octet, we got an octet, we're done. Right. The tools we use, I'll tell you, you know what oxidation states are? If valence bond was quantum mechanics light, oxidation states is quantum mechanics, you know, kindergarten version to make your life easy to, you know, to try to get a picture of this, right? I mean, we're very, very much oversimplifying the atom so that we can see a picture, but we're doing it with a purpose. We aren't just making a simple picture. We're saying if the electrons were distributed like this, then these are the charges that would result, and this is what I expect for the electron density. If the electrons were distributed like that, you know, and those are the two extremes. It can't go beyond that. And so we know the real picture is somewhere between. If we wanted the exact real picture, we would do the full treatment. But we don't want to do the full treatment because on a test, they aren't going to allow you to have a computer, right? And you don't want to use a computer to solve every single problem. So this is why. You know, if you're trying to think, okay, why? What is the whole idea why the whole idea of trying to understand formal charge and oxidation states is because of this. It's going to make your life simpler. And that's what we want. Right? And so that's why we use it. And so if somebody asks you, well, what is formal charge? You know, just be able to tell them. What is oxidation state? You know, this is trying to get a visual picture of the structure of what's happening. And so, but you know, like anything else, when you oversimplify it, there are some, yeah, you got to use some judgment in how you analyze it and the data. And so this is why and then this is why I want to finish, because I just want to finish acetic acid right now. What I want to do is, I want to say this. This is oxidation states preschool level, let's say. The reason why I call this oxidation states preschool level is because it's too oversimplified. It's too oversimplified because of this. What's the oxidation? Which one do we do first? Hydrogen, carbon, or oxygen? Hydrogen gets +1. Actually, let me make this bigger because it's hard to see. Yeah, let me know if my writing gets too sloppy or if you can't read something. These pens are... Okay. Hydrogen gets +1, and then what goes next? Oxygen at -2. Carbon is at 0. And so these are the apparent charges on the atoms if you assume ionic bonding. So each oxygen would be at -2. We got 2 of them. Total charge would be -4. We have hydrogen at +3, so each one at +1, so we have 3 of them. So the total positive charge +3, -4 plus 3 is -1. +1 is 0, and this whole thing's 0. So it works, right? But the reason, though, that I call this the preschool version because it's too oversimplified. It's too oversimplified because of this. It averages the oxidation states. And so I asked you to determine the oxidation states on acetic acid from the Lewis structure. So let's do that. And then we'll go on a break. 15 minutes. Carbon versus hydrogen, who wins? Carbon. So this is simple. Only one rule. What's the rule? Winner takes all. Oops. I forgot this one. Carbon versus carbon. Which one's going to be the winner that takes all?
Actually, it's going to be a second.
Yeah, you'd think it'd be the second one because you're right, the electronegativities are different. But when we count oxidation states, it's going to be a tie. It's not really a tie, you're right. But we're going to call it a tie because that's the way we count oxidation states. And so carbon versus carbon tie, we can't help it. So you got to know that. All right, so how many did carbon end up with?
7.
How many is it supposed to have? 4. And so it's got 3 extra electrons. The oxidation state is -3. So which one is right? Do you see we have a conflict? Is carbon 0 or is carbon -3? Carbon's -3, so is that wrong? No, that's not wrong, because what's the next carbon?
+2.
Yeah, the next carbon only has 1 electron. It's supposed to have 4. It's missing 3, so it's +3. And so what's the average oxidation state on carbon? 0. And so when you do the rules in chapter 3, you get the average oxidation states. Average oxidation states are useful because they're quick and easy to get, but they aren't going to be as useful as this because this shows you that these 2 carbons are different in properties. One of these carbons we call electron rich because it's got a lot of extra electrons. This carbon we call electron poor. And so here, you know, this is, it's just even. Neither rich nor poor. But that's not the case. And in chemistry, we're looking at how the atoms interact and how the molecules interact. Then we want to know this. We don't necessarily want to know this, although this can still be useful if you want the average. You know, especially for big molecules. For very big molecules, drawing the Lewis structure is a pain, so you might just get the average instead, right? And then this. And so this would be the more advanced version, but you know the more advanced version is easier. It's easier. The only pain is you have to draw this structure. And so let's look at two that we were looking at earlier. Hydrogen peroxide. And figure it out. Okay, hydrogen versus oxygen. Oxygen versus oxygen. How many electrons? 2, 4, 6, 7. It's supposed to have -1. Hydrogen has 0. It's supposed to have 1 plus 1. You see? Now for sodium hydride, we have something like this. You know, sodium has how many valence electrons? 1. Hydrogen has how many valence electrons? 1. And so let me draw it like this rather than draw a line, because a metal and a non-metal typically form ionic. And so I'm going to draw it like this, but we got to figure out who gets the electrons. What's the electronegativity of sodium? It's like 0.9. What's the electronegativity of hydrogen? 2.1. Who's the winner? Hydrogen. Winner takes all. And since this is an ionic, metal and non-metal, we say sodium with no valence electrons plus, and hydrogen with 2 valence electrons minus. Sodium hydride. Do you see the, actually the more advanced levels actually, I think is actually easier because it's just so simple, right? Whereas the less advanced level, you have to memorize all the exceptions. Now with the less advanced level, in Chem 4, they often give you the what they call the easier. You know, in Chem 4 or Intro Chem, they give you the easier method, but the easier method has a lot more exceptions. And so the only way they make it easier is by never giving you an exception. And so it always works. And this is, you know, this is often done. I remember being in science, and I used to not like that because, you know, they never told us the exceptions. And they just said, oh, that calculation's easy, but the but part was missing. And so then you get to more advanced classes and you remember that. I remember that equation. It was so simple. I'll just use it again. But you use it for the wrong thing. This happens every semester in Chem 1A. Every semester in Chem 1A, you're taught, well, I don't know why they do this, but for the titration. Do you remember the titration lab in Chem 4? If you had Chem 4 here, this is not what you're supposed to use for titration. But in the titration lab, they have this equation here, and I need to change that because it's not right. And so they calculate the molarity of their unknown using this equation. Well, that's wrong. You know, even though they used it in Chem 4, and I got complaints. You know, I used this in Chem 4. Why is it wrong in Chem 1A? Well, it's wrong in Chem 1A because they didn't tell you the exceptions. You know, it doesn't work. Okay, we'll stop here and then we'll take a 15-minute break.